below this extending leader. And it acts as kind of a transition region, or kind of a buffer between the conduction current that flows here and displacement current that flows in the air. And presumably this region is the source of VHF and VHF radiation. This is for positive leader. And the streamer zone is kind of simple, just a bunch of streamers hanging from the leader tip. For negative leader, the streamer zone is more complex. It usually involves a so-called space stem. I'm going to discuss it later. And both positive and negative streamers developing in opposite directions. VHF radiation is widely used for producing lightning channel images. And there are two main technologies. One is called interferometry, and the other one is called time of arrival. And shown here is an example for the time of arrival system, LMA, light mapping array. And this is the formula they usually use. The plan view here, to elevation use here and here. And finally, altitude as a function of time. This was a bi-level, so-called bi-level cloud discharge that shows a vertical channel that was formed first. Here you can see a function of time, blue color corresponds to the earliest processes of the flash. And then the horizontal extensions in the positive charge region, negative charge region. Usually, what is imaged using this method or this kind of system, LMA system, is negative breakdown. So positive leaders, positive streamer zones, they usually radiate very little on VHF. However, it is still possible to image some positive leaders, and this is an example taken from a paper by Yoshida published 2010 for rocket-triggered lighting. And what you see here at the bottom on an 8 millisecond time scale is the initial stage current. Those kind of unusual. The current magnitude is some kilograms, usually some hundreds of times. This is an order of magnitude larger. And the top two panels, they show the same current, but just 2 milliseconds here in this region, the highest levels, and the corresponding VHF sources, altitude as a function of time. This is 2 milliseconds. This is 2 milliseconds as well. And in this case, the broadband interferometer developed by Osaka University, was used, and the sources were propagated upward. The corresponding currents again were in kiloamps range. So if positive leader produces sufficiently large currents with impulsive components, as seen here, it will radiate as strongly on VHF as negative. Also, LMA normally has baselines of the order of tens of kilometers. And if you make a compact LMA, then it is possible to image positive leaders reliably. We currently have an LMA operated at Penn Landing, and very nice images of positive leaders are recorded. This is an animation. I'm not sure if it will work. We'll find out. I don't know. There is no touchpad, there is no mouse. There must be something, right? So if you click on the image, yeah, okay. This is a time of arrival system, LDAR, similar to LMA, that operated in Texas, in the United States. And this is a very unusual lightning discharge. The spatial scale is indicated here, 50 kilometers from here to here. So many tens of kilometers overall extent. Also very long. The time scale is here in 3 seconds. An interpolation algorithm to connect individual located sources was used here. That's why it appears to be kind of continuously developing. Unusual discharge, it produced 2 positive strokes to ground at this time, and at this time 2 red dots, and 2 negative strokes to ground. Green dot here and green dot here. And if you can play it one more time real quick, so you can try to detect where spikes to ground were produced during this 3-second long light flash. The strongest VHF HF and VHF radiation is produced by so-called compact intracloud lightning discharges, or seeds. They're called compact because the channel length for these discharges are of the order of hundreds of meters, significantly shorter than length of channels of cloud-around discharges, or particularly cloud discharges, which could be many tens of kilometers long, as we saw in the previous application. So these compact intercloud discharges, the most intense nature produces HF and VHF radiation in Earth. They tend to occur at high altitudes, mostly above 10 kilometers. They appear to be associated with strong convection and tend to produce less light than other types of lightning discharges, as observed by Forte satellite. And they also produce single bipolar electric field pulses, so-called narrow bipolar pulses. And the amplitudes of these pulses are comparable to those produced by neutron stars. So very intense events. Some examples: electric field signature, magnetic field signature, or single compact intracloud discharge. The corresponding DED signature measured independently, and finally the VHF signal shown here, 46 megapercent frequency. And this signature is very large. You cannot appreciate it from this slide, but I'll show later the comparison. It will be clear. The majority of these events are isolated. Probably 72% estimated in Florida are isolated. There are no other lightning processes hundreds of milliseconds before, hundreds of milliseconds after. Some of them occur at the beginning of cloud discharges, and they appear to contribute somehow to the initiation of cloud discharges. Some, approximately 6% in our data, are associated with cloud-to-ground discharges. And one such example I'm going to show next. So what you see here are two traces, a vertical electric field, and this is a VHF, corresponding VHF signal on 400 millisecond time scale. This was a multi-stroke cloud-to-ground discharge. Strokes from 2 to 7 are shown here. Actually, there were a total of 8 strokes in this case. And there was one compact cloud discharge that occurred between strokes number 3 and number 4. This is an expansion of the compact cloud discharge. If you look at this record, it is not very impressive. It's pretty large. However, return stroke field changes are much significantly larger. And if you look at the VHF record, all the return strokes are tiny. They're all dwarfed by VHF signature of this compact cloud discharge. Another interesting thing about this event is illustrated here. This is a plan view of locations for all the 8 cloud-to-ground strokes and for the compact intercloud discharge. Strokes from 1 to 3 all occurred before this seed. They occurred here in this region. Then seed occurred after stroke number 3, 7 kilometers away horizontally. And after the stroke number 4 occurred here in a different channel. And then strokes from 5 to 8, they returned back to the original location. So maybe this seed somehow influenced the course of this cloud-to-ground discharge. The next topic is electric fields measured in the immediate vicinity of the lightning channel. This was a joint experiment with GRIP in Japan. Dr. Megumi Miki, he spent 1 year at the University of Florida, and he brought his motor sensors, crystals changing their refractive index in the presence of external electric field. And this is the holder, plastic holder, and the crystal is right here. This is a vertical strike rod where a lightning channel is supposed to terminate. And the distance from the tip of the strike rod and the focus sensor was 10 centimeters. Some very interesting measurements were obtained, and I'm going just to show 2 slides with some selected results. For rocket-triggered lightning, we measure currents routinely, so current in the lightning channel is known. If we knew the longitudinal electric field in the channel, then the product of current and electric field would give us input power per unit channel. And if we integrated that power over time, what would be energy per unit channel length? It's not possible to measure, or virtually impossible.